So I have the joy of welcoming you all. Thank you for attending today. And my name is Lisa Stewart. I am Chief Administrative Officer at the Kavli Institute for Theoretical Physics. We're in Santa Barbara, California. It's my honor to welcome you for today's talk by Dr. Carol Scarlett, who is presenting this talk for the National Society of Black Physicists Innovate Seminar Series. This series, by the way, is one of the only items on my very short list of good things that have happened in 2020. I am actually sporting my NSBP annual conference t-shirt that I got in the mail last week. And thank you, NSBP conference planning team. And congratulations on hosting a magnificent virtual conference this month. Today's Dr. Scarlett's talk will be approximately 30 minutes. And we're presenting in a webinar format, which means in part that we will hold questions until the end. So please, as questions come up for you throughout the talk, enter those into the Q&A directly so that following our talk, Dr. Scarlett will try to address your questions as the time permits. And then next up, I would like to introduce you to Farah Simpson. She is the leader of the NSBP Student Council, which is also the group responsible for creating and leading this Innovate Seminar Series. Thank you again for joining us today, and we hope you enjoy Dr. Scarlett's talk.
Thank you. Farah, you had something?
Yes, so I just want to say hi, everyone. Again, we are pleased to welcome you to another Innovate Seminar Series talk. The Student Council has worked very hard on this series, and we're so glad that you are all enjoying it. Dr. Scarlett actually serves as the Technical Executive Officer on the NSBP board, so we are particularly excited for this specific talk. Dr. Scarlett is currently an assistant professor at physics at Florida A&M University, and she's involved in dark matter research as well as developing a program to use positrons to study plasmas and weak interactions. Her research group is also involved with a measure of the weak interaction cross-section for a positron on a neutron. So with that, I'd like to present Dr. Carol Scarlett. We hope you enjoyed the talk. Thanks.
Thank you so much to both Lisa and Farah. Thank you for that wonderful introduction, and thank you for giving me the opportunity to speak at your program. As Lisa has said, I do exotic particle searches. I do dark matter searches, as also Farah echoed. And I want to talk to you a little bit about a novel way that we can look for exotic matter. With that, I am going to share my screen. And so the title of my talk is Axionic Dark Matter, New Search Techniques. And that's mainly what I'm going to focus on. And to keep this down to about half an hour, I have more slides here than what I'll actually talk to. But just to start out, this work was being done in collaboration with both Dr. Sturrock out of Stanford University and Dr. Fischbach out of Purdue University. And there are actually several other names that should be on here, but I didn't have time to list them all. And this work involves looking at nuclear decay. But before we get to looking at nuclear decay, let me just give a little background, history, and some motivation. So I'm going to talk a little bit about the idea of an axion. This is an exotic type of particle that was originally theorized to solve the strong interaction CP problem. This is the charge parity problem. This is a type of transformation in quantum mechanics for all of you who've gone through a first year, second year of quantum mechanics, and maybe even graduate level. There are specific transformations that you can do, and it is found that weak interactions violate CP as a symmetry, but strong interactions do not. And I'll talk more about that and talk more about why this type of symmetry and symmetry breaking gives rise to particles and to this theorized dark matter candidate. Now, in more recent times, of course, in addition to the CP problem, there's a problem with cold dark matter in the universe. That is, most of our galaxy appears to be made out of a particle that does not interact with electromagnetic fields. So it doesn't block out light. It also doesn't produce light. So it's not baryonic matter. And scientists have had many theories on how this type of particle would interact. Dr. Fishbach, who I mentioned earlier, he happens to be someone who worked under a man named Primakov, and Primakov came up with a mechanism for exotic particle coupling that allows us to take what we believe to be the particle which is creating the CP problem and apply it to dark matter physics. And lo and behold, the axion appears that maybe it'll solve both. Normally, I would tell you about some of the past experimental searches for dark matter axions, but I think for this particular talk, I am going to skip over, sort of gloss over those. I'll just briefly mention them because I want to get into the next item, which is decays, nuclear decays, and the fact that we may actually be seeing signals of axionic dark matter. And even if we're not, nuclear decays may be the best place to look for axionic dark matter. Okay, so in physics, everybody learned that there are conserved quantities. So from the start, everyone hears maybe around 5th grade or so that energy cannot be created or destroyed, matter cannot be created or destroyed. So there are certain fundamental things we say that they're conserved. They're there all the time. If I take a piece of paper and I tear it into little pieces, I might not be able to read what was written on the paper, but the paper itself is not destroyed. It's just chopped up into little pieces. And if you weigh the little pieces, you'll find they weigh exactly as much as the original piece of paper. And so therefore, matter is not destroyed. All of these symmetries, though, can be expressed in mathematical equations. It turns out that these symmetries fundamentally mean that there are certain parameters that if we shift them, we make certain transformations. Those transformations don't change the physics of our equations. So energy conservation. Energy conservation, we write down a Lagrangian. A Lagrangian expresses energy. And we find that if we make a coordinate transformation, that is, if we simply change the origin of our coordinate system. So instead of putting a particle at the origin, if we put it 1 meter away from the origin, so we call that the unit 1, that making this sort of transformation has no impact on the math, has no impact on how much energy the object has. So an object measured to fall, free falling gravity in Florida, is going to free falling gravity the same in Illinois, free falling gravity the same in New York. There is a conservation of energy as a result of the fact that there's no special origin. We can't simply change the position of an object and suddenly we observe that its energy changes differently. Okay, so that's what energy conservation is in a mathematical sense. So also, that leads to momentum conservation. So in momentum conservation, you have the same phenomena. If I change the position of an object, I find that that does not have any influence on the momentum. This is what we call homogeneity of space and homogeneity of time. That means space is basically the same through and through. There's no special points in space. And also that time is basically the same through and through. Now, someone will debate me on general relativity. We can talk about that later. General relativity doesn't change energy conservation. And so fundamentally, energy and momentum conservation, these things that we observe, that you can't simply make things disappear or make things appear, fundamentally, they have to do with what our space and time look like. These are homogeneous space and time. Okay? In fact, all classically conserved quantities, energy, linear momentum, angular momentum, they're all associated with some sort of symmetry. When it comes to quantum mechanics, now we're dealing with things on an infinitesimal space, we find that similarly, all of our quantum mechanically transformations that are conserved also turn out to imply a symmetry in space. So with parity, this is the idea that I invert one axis, and you can think of it as a left hand and a right hand. And a parity transformation would turn my left hand into my right hand. For a long time, it was assumed that, hey, in the mirror of space, nature shouldn't have any preference. So a left hand is every bit as good as a right hand and vice versa. There's no reason for nature to have picked out one versus the other, which means even though I can't geometrically, physically twist my left hand and make it look like my right, because it's an inversion, that inversion should have no impact on how objects move and change in space. This turns out not to be true. But this is how scientists thought for a very long time. Same thing with charge. If I had called an electron a plus charge and I called a proton a minus charge, who cares? Shouldn't make any difference, right? And so changing the electrical charge on an object, this is just a word, it's like moving the coordinate system, shouldn't make much of a difference. That too turns out not quite to be correct. And then finally, time reversal. On a small scale, if A and B can combine to make C and D, then C and D in particle physics, all of particle physics, has the same probability and cross-section to combine and make A and B. And so on an infinitesimal scale, there's no such thing as an arrow of time. Anything that can happen can spontaneously unhappen. The arrow of time comes about only on a macroscopic scale where you have lots of particles involved. So these are the quantum mechanical symmetries that I'm talking about. Everybody's familiar with the classical conservation of energy and momentum and whatever. The quantum mechanical symmetries you may be less familiar with, but these are transformations. Again, this is math. You go apply an equation, you apply a parity transformation, a charge transformation, and you assume that the dynamics of your system don't change. That was until about 1950, when Madame Wu did an experiment on cobalt-60. The assumption was that a cobalt-60 nuclei that was propagating in some direction and spinning about that axis, that if the cobalt nuclei propagated in the same direction but spun with the opposite handedness, so if it propagates up and I have a left-handed system, and it propagates up and I have a right-handed system, you'll notice they spin in opposite, they curl and spin in opposite directions. But you think, nature shouldn't care about that. It doesn't, absolutely shouldn't make a difference. If you observe a decay in cobalt-60 nuclei, that decay should not care whether it was spinning clockwise or counterclockwise. Well, in 1950, Madame Wu did the experiment to see if that was so. And lo and behold, it turns out there was a huge asymmetry in the number of nuclear decay if the system were spinning such that it was a left-handed system versus if the system were spinning such that it was a right-handed system. It turns out nature cared a great deal about handedness. I'll tell you, for anyone who's done chemistry and you've heard the word chirality, which refers to handedness, you'll quickly recognize that in chemistry, biological molecules, say you have a hydrogen, an oxygen, a carbon, and a nitrogen, and they're going to bond. And they bond in such a way that they make a left-handed molecule. Your carbon sticks out, your hydrogen, nitrogen, and oxygen are in the plane. And then you flip your carbon to stick out in the other direction with your hydrogen, nitrogen, and oxygen in the same order. And you say, hey, nature shouldn't care about that. If I have a vitamin that combines these two, shouldn't make a difference. You learn very quickly that that is absolutely not true. The human body absorbs almost 90% of one and not the other. In fact, most of the DNA molecules, most of the amino acids, it turns out, have a particular chirality to them. They have a particular twist, and they don't have the opposite twist. So it turns out that not only in fundamental physics is this notion of handedness, this symmetry violated, it's broken, because it's not correct. If you apply this symmetry and you think you're going to get the same equation out, you find out very quickly that nature doesn't work that way. But it turns out that on a larger macroscopic scale, this works that way for biological tissue and for lots of systems. So nature does have a preference for handedness. And now we know some things that we fundamentally believe to be true based on math may have led us in a not right direction. It was assumed afterwards, though, that, okay, maybe parity is violated, but if you flip the electrical charge in your equation, this goes back now to CP, that maybe CP is a good symmetry. And I will tell you, as someone who's studied particle physics and kaon decays, it turned out that the weak interaction not only violates parity, but it also violates charge parity. So if you apply both of these transformations thinking, well, you'll recover a good equation, turns out you don't. Now, all of quantum mechanics hinges on this notion that CPT, that is a transformation of charge, parity, and time, must be a good symmetry. In fact, all of your Lagrangians are written to be CPT invariant. So the assumption is, well, if charge and parity can come out opposite, meaning I apply a charge parity transformation and I get a flipped sign, then the only way I can recover and get back the same thing, two negatives multiplied makes a positive, is I also have to have a time reversal violation. That is, on a particle scale, now that we've observed charge parity violations, we think we're going to have to observe in some system that there is an arrow of time. It is not simply a macroscopic phenomenon. To date, we've not observed this. And in fact, lots of scientists, lots of nuclear physicists, this is where I started my nuclear physics degree, have searched for time reversal violation. One place that you could observe time reversal violation, should it exist, would have been the neutron or a nuclear system. And here's why. In a nuclear system, you have quarks. And in a neutron in particular, your quarks add up to a net charge of 0. So you have two positive 1/3 quarks, and you have one positive 2/3 quark, that's your U quark, and two negative 1/3 quarks, two D quarks. And together they add up to 0. So naively, you might think, well, if I have two negative charges and a plus charge, and they're physically separated in space, that's a dipole. That would give a neutron an electric dipole moment. So here's why a neutron with an electric dipole moment would be T violating. That is, under the reversal of time, it wouldn't hold up. And in a second, I'm going to get to axions and why they have to be brought into this picture. So in this picture, you naively say, well, my neutron system with its plus 2/3 and 2 minus 1/3 charges, that looks like a dipole. And now what happens in time? The neutron has angular momentum. So the neutron has a spin, just like the proton, just like all the fundamental particles. So if I reverse time, I will automatically flip the spin. That is, I will flip a left-handed system into a right-handed system. A system that curls to the left now will curl to the right under the reversal of time. Something moving in the clockwise direction has to move back in the counterclockwise direction. However, the electric dipole moment won't flip because the electric dipole moment is only governed by a separation of electrical charges. And since it's governed by a separation of electrical charges, just reversing time doesn't move it in any other direction. This would mean that under a time reversal, I would have a separate set of systems for any neutrons. Neutrons couldn't be a single system because under time reversal, I would now have a neutron with an EDM aligned with this spin and an EDM anti-aligned with this spin. Therefore, I would have to have time reversal violations in a neutron system. Well, nature got out of that. Nature doesn't allow you to ever see down to 11 orders of magnitude and neutron EDM. So even though a neutron is fundamentally electrical charge is separated, to date, down to 11 orders of magnitude, there's been no observed neutron EDM. And then that brings us to QCD, quantum chromal dynamics, and the fundamental Lagrangian and why this thing does not violate CP symmetry. So what that means is that in your neutron system is made up of quarks, but those quarks have in the space between them something called instantons. These are objects that come into and out of existence, sort of like a little boiling sea, like the image that you see here. And what's happening with these instantons is they're not allowing you to ever measure that your quarks are physically separated in space. So when you do a dipole experiment on a neutron, you don't find anything. Well, to make that work, Pecci and Quinn proposed that these instantons must have an additional field or must be coupling to an additional field called the Axion field. So in quantum dynamics, quantum chromodynamics, whenever you have a phenomena that pushes or pulls in some direction, you have to associate some field with it. Whenever you have a field associated with the phenomena, you have to associate a new particle. So Pecci and Quinn proposed that there would be this additional axionic field, and therefore the axionic particle was born in order to explain why the neutron has no neutron EDM and why we don't observe time reversal violation. And that would have been good enough. You then put this in your Lagrangian. You would then say, okay, this is an estimate for what my neutron EDM should be. It's 11 orders of magnitude too big, and we don't observe it because of this additional particle and this additional field. But it turns out that the theorized axion isn't just good for explaining charge parity violation. The theorized axion is a weakly interacting particle that couples to quarks and that would couple weakly to photons. That is, there's only a couple ways in which it would interact, but not directly with a photon. And so therefore, the axion particle, this additional field, which is causing your neutrons to never show their EDM, has to exist and permeate all of space. That means it has to exist in our galaxy. That means it's a good candidate for the additional mass that we need in order to create our galaxy in the first place. So if anyone is into dark matter or astrophysics or astronomy, you probably know more than I do about gravitational lensing and about Einstein's general relativity and how very massive galaxies are actually bending and curving space. And so here's just an example of strong gravitational lensing. And this comes about not because of the luminous matter, the very light objects that you can see here. This comes about because there's a whole lot of dark matter sitting in any one of these galaxies, so much so that they weigh so much that galaxies behind them that we shouldn't be able to see, the light from those galaxies are bent and curved, and we see fragments of it. In fact, our own galaxy should never have formed. The stars in our galaxy simply don't have enough mass and to have ever formed a galaxy in the first place. The stars are moving way too fast. And so you need dark matter, you need some additional mass in order to pull this material together. And so that's where your axion comes in. Your axion would be this particle that permeates space, that interacts with your neutrons, interacts with your nuclear matter. As a result, it prevents your nuclear matter from having these electric dipole moments. At the same time, there's so much of this additional matter that you also get enough mass to allow galaxies to form. To date, there are about 19 galaxies that don't appear to have dark matter. That is, those galaxies have stars that are all moving at the right velocity, that the stars themselves account for the rotation curves and account for how the galaxies look. Interestingly enough, 2 of those galaxies, and I'm not sure of the other 17, I don't know how they've been weighed yet, but 2 of them only have 1/200th the number of stars as our galaxy. So while those galaxies have formed, and the stars that are hanging in those galaxies appear to be coupling to the luminous matter in those galaxies are only a small fraction, 1/200th, the mass of our galaxy. And so as a result, you could imagine that anything that formed that was moving too fast has long escaped those. And so we have a lot of evidence that there's some additional mass in space, and the additional mass could account for how matter behaves on an infinitesimal particle scale, but also how matter behaves on this grand cosmological astrophysical scale as well. So that's what makes axions as a candidate and as a particle really very interesting, and why there's been a renewed attempt to uncover the properties of these particles. I happen to be an experimental physicist, so I'm always looking at these type questions and thinking to myself, how do we design an experiment to see these things? Okay, and so what I'd like to do is just briefly mention that there have been to date a number of experiments that have attempted to directly detect axions. Some of them have been in accelerator laboratories like the ones that I've worked in. Some of them have been in smaller laboratories. To date, nobody has claimed convincingly that they have detected an axion, that they know exactly what the axion's mass is, and they know exactly how that axion couples to other particles, okay? And in fact, to date, we've been able to rule out a lot of range as far as mass and coupling constant. And let me just say a few words about how that works. So now that you have this axionic dark matter particle or this dark field, and you say, okay, this may be accounting for the additional mass in our galaxy, the next thing that you have to think, well, what does this object weigh? I mean, what does each little piece of it weigh? Like, we know that we're all made up of protons, neutrons, and electrons, but we know that the individual electrons weigh 1/2000 the mass of the proton, and the mass of the proton plus the mass of the electron is roughly the mass of a neutron. And so you can ask yourself, well, what would be the relative mass of these other little objects? Are they the mass of the electron? Or are they much bigger, the mass of the proton? And so lots of scientists have put tremendous amounts of time. One of the places that we find very helpful are stars. So if you have this axionic particle, many of you may be aware that in photonic interactions, photon is a really weird object. The photon can fly through space and then spontaneously convert into a massive particle-antiparticle pair. Usually, unless it's hit or collided with something, that particle-antiparticle will annihilate, so you'll just have a tiny fluctuation in space. And this gives rise to photon-photon scattering, which is also something that's rarely observed, but has been observed. Well, the photon could fluctuate into a massive axion and an anti-axion as well. And so this gives rise to the notion that if your axion has a certain mass, you would see it because your stars that produce lots and lots of photons, and those photons move through very dense matter in order to escape. Well, those photons would collide with material within the star. They would turn into axion, anti-axion pairs, and you would have a mechanism for bleeding energy out of the star. Just like when you have stars fusing protons and neutrons to make heavier and heavier atoms, or the nuclei, in the process, they make neutrinos. And since neutrinos are weakly interacting, once a neutrino is made, it can escape from the star, and this bleeds energy out of the star and causes the star to age. That is, the star is changing in a way that it can't seem to change back from. It's on its way, it's always aging and moving through a certain process because it's losing energy in a way that it simply can't get back. Well, axions are another particle that would do that as well. And so thanks to astrophysics, us particle physicists are able to put a lot of limits, okay? And then here's just an example of that solar interaction I was just telling you about. Now, I will fast forward through some of the different mechanisms for using photon interactions in order to get at axions, that is, in order to see dark matter. And I'll gloss over some of the Lagrangians. These things are things that anyone interested can very readily look up. Photon interact with axions would lead to a birefringence in space. And this birefringence is something that light experiments have sought. Many of these experiments I have here are some of them. So let me get to how do we detect. So the graphs that I was just showing show that the axion and photon will couple to one another. And as I said, this would lead to stars losing energy through the manufacturing of axions. And because of that, this has led a lot of scientists to attempt to uncover axionic dark matter through laser experiments. So we propagate lasers through an electromagnetic field, a magnetic field that's oscillating. And in the process, we look for the laser light through the magnetic field to interact with these axions, and that would cause the light itself to deviate. So that's one mechanism. And then here's those deviations lead to birefringence. You can induce an ellipticity change in your laser beam. You can have a dichroism where one direction of laser light, one polarization direction is selectively absorbed. And then as a result, this would allow you to optically detect the presence of your axionic dark matter. Now, these experiments have been done since like the 1980s. They started out at Rutherford, and the laboratory where I once worked, which is Brookhaven National Laboratory, also did several of these experiments. And to date, they found some spurious signals, but nothing that they could prove definitively was related to an axion. And then this is one of the old experiments, one of the first experiments that was done by a very good friend and colleague of mine, Yanis Surmatidis, in 1989, and they were searching for ellipticity changes. So this is one method for looking for this exotic particle. And understand that as an experimentalist, the thing that we do the most is come up with ways to make something that's been theorized to exist, to make it interact in a definitive way so we can say that it was there. Sort of like we are shining light on it, in a sense. Okay, and then here's some additional experiments. CERN has an experiment called CAST, which is a axion cavity search. There's another experiment out in Washington State, ADMX, which is also a cavity search. And then there was an experiment, PV-LOTS, which was a spinoff of the 1989 experiment done at Brookhaven. And again, to date, they've all put limits on the mass and coupling strength of the axion. But as you can see in the previous graph, if I could flip back to it, while they put limits on it, there's still some range for axions to exist. And so this is axions still are one of the preferred dark matter candidates because there's still mass and energy ranges where it could exist. And it's one of the few objects that would explain not only nuclear physics, what is being observed in nuclear physics, but what's being observed on a cosmic scale. So it makes it sort of a really neat, fascinating object to search for. But now that I've told you a little bit about some of the earlier searches, which involve optics and lasers propagating through space and hoping that those photons will bump into axions and be transformed in a way that you can record, let me turn to another phenomena. And this is the phenomena of axions coupling either to photons or to nuclear objects and leading to sort of a annual oscillation in how those objects, the dynamics of those, like how neutrons decay or how an annual oscillation in, say, certain types of experiments, which I'll tell you about in a second. So about a year ago, I had this really great idea as I was thinking about experimentally how you could design a search for axions and realizing that, hey, we're moving through not just around the sun, but we're moving through the galaxy. We're recoiling through the galaxy at a certain rate, about 500,000 miles an hour. The Earth moves around the sun at about 70,000 miles an hour, and then it spins, of course, if you're near the equator, it spins about 1,000 miles an hour. So with all of this motion, you might expect that there are going to be times during the Earth's annual cycle where you're moving into the galactic axions. That is, you're moving against them, and therefore you have a higher relative velocity. And then there are going to be times when you're moving in the same direction as the galactic axions. And so therefore there would be times when you would have a slightly lower relative velocity because two objects moving in the same direction are going to have a lower relative velocity. So therefore, there may be an annual signal that you could look for in just some things like nuclear decays or even in some other signals that might indicate that it's due to this axionic dark matter that you're moving through. Much to my chagrin, a woman by the name of Katie Fries, who I had the pleasure of meeting while I was a graduate student at the University of Michigan. Well, Katie Fries had that idea about 30 years ago. In fact, I was pleasantly surprised to find that her and some colleagues had over 30 years ago written about looking for this annual oscillation in various systems. And these could be electrical systems, these could be in laser systems, these could be, as I mentioned, in nuclear decay, but these sort of annual oscillations that would be due to the fact that you're moving through this additional mass, so you're sort of dragging through it in at one time of the year in June, and then at the other time of the year you're moving in the same direction. So it's called a WIMP wind. WIMP stands for weakly interacting massive particles. Axions are just one type of weakly interacting massive particle. There are theoretically other objects that could also be candidates for dark matter. But I like the axion because it would solve the charge parity problem in nuclear physics while simultaneously solving the mass problem in cosmology. Okay, so one of the things you could also think about is, the fact is annually, if you're going to look for some annual oscillation, here's where an experimentalist has to be careful. Annually, the biggest oscillation, of course, is the amount of sunlight hitting the ground. So you do have an annual oscillation just due to the fact that the Earth spins on its axis. And if you're in the northern hemisphere in December, you are rotated away from that sunlight, and therefore you're getting a smaller signal. In June, of course, you are rotated towards that sunlight, and therefore that's when we have our summers. So as an experimentalist, this is where sort of the rubber meets the road. You have to think that, well, but there are lots of annual signals, and some of those might be smeared out due to something like solar oscillation. Some of it would be smeared out because not only do you have solar energy coming down on the Earth, but the Earth actually bounces back pretty much its entire solar intake on a daily basis. This is called the albedo radiation or downwelling radiation. That's the energy that the Earth has to bounce back. Otherwise, that radiation gets trapped in the Earth's atmosphere and you've got massive global warming, which we don't want. So we want the Earth to bounce back pretty much everything. So all of these are going to produce annual oscillations. Now, the question is, do those solar and albedo radiations, do they impact, what systems do they impact? And do they smear any potential results? So as someone who started out in nuclear physics, who started out doing time reversal violation searches, and as someone who is interested in looking to nuclear physics to solve or to find these axionic dark matter particles, I went out and found data from the Geological Survey Institute of Israel. And lo and behold, this institute was looking at radon decay, and they found this nice daily and annual oscillations. Now, nuclear particles in general do not follow the sun. They do not care about solar radiation. And the reason that they don't is that nuclear objects tend to require very high energy, usually keV, these are thousands of electron volts or millions of electron volts of energy, MeV of energy, in order to stimulate any sort of nuclear transitions. So nuclear interactions tend to be oblivious to solar radiation, which is about 1 electron volt, maybe up to a few electron volts, or to albedo radiation, which is even longer wavelength. Most of it's actually heat. The ground heats up during the day. But seeing these oscillations did make me think, look, if I look at solar and albedo radiation, and I look at how these radon decay data from GSI look, then what I find is the radon decay data, this blue curve, is basically a dead ringer for a vector sum of solar and albedo radiation. And if any of you, those of you who are physicists who may have, who know about particle interactions, know that there's almost nothing that should ever look like a vector sum of two radiation fields. And the reason nothing should look like a vector sum of two radiation fields goes back to that photon-photon scattering picture that I showed you earlier, where photons simply pass through one another because they're bosons, and they don't really interact. So if they don't interact, you should never get one photon field canceling or interfering with another. Yet when you look at the radon data, lo and behold, it looks just like what you would expect if you took a vector sum of your solar and albedo radiation. Additionally, if you take a vector sum of your solar and albedo radiation, it makes a prediction for a little small peak that turns out to show up in the data. And so looking at first glance at what is going on in the radon decay data seems to hint at photons behaving in a way that, as an experimental particle physicist, we know that they just don't behave. And one of the possible solutions is something called a Primakov mechanism, which would allow these photons coupling through dark matter to alter nuclear decay. And so, in conclusion in my talk, I want to say that while we don't have an independent verification yet of GSI, which is something I'm working on, the GSI data and the radon data is really interesting in that it has all of the right ingredients to be a possible signature of axionic dark matter in the nuclear sector. And on that note, I will stop sharing and gladly take some questions.
Okay, so just a reminder, please enter any questions that you have into the Q&A chat. So we have two questions right now. The first one is, when you said that the strong CP violation is allowed only at the level of 1 part in 10 to the 11, do you refer to the limit on the theta angle in radians or something else?
Oh, I'm not saying that it's allowed at that level. I'm saying that what I'm actually saying is that to date, when people have attempted to measure the EDM for a neutron, if you estimated the electric dipole moment of a neutron by naively assuming that the neutron itself is at the scale of about a femtometer, so 10 to the minus 15 meters, and then you take the quarks and you say, okay, you have two negative a third and a plus a third, they're separated by roughly a femtometer, you would come up with an electric dipole moment of about 10 to the minus 16. You'd come up at a scale of about 10 to the minus 16. And what you find when you try to go and measure it is that scale is too large by 11 orders of magnitude. So when I talk about why we have a CP problem, what I'm really getting at is that if I were to naively assume that I could treat my neutron the way I would treat any other separated charge, I would get 10 to the minus 16 electrons per femtometer. Then I find out that that scale is 11 orders of magnitude larger than what experimental limits have placed. So you go do an experiment and you find if you could see down to almost a trillion of that scale, which is what we've been able to do, you still fail to find an EDM. So in case it wasn't clear, I wasn't referring, well, it does refer to the angle theta too as well, because the angle theta then is your assumption for how you would project that EDM onto space. And you would say that down to 10 to the minus 11, you know, you can't find any sort of projection of an electric dipole moment onto any space where you measure it. but it's really that the electric dipole moment is that many orders of magnitude smaller than what you might naively assume it should be.
Okay, thank you. The next question is, for the Axion mass limits plot from different types of experiments, do they assume the coupling to be unity? How is the sensitivity of these different types of experiments for measuring the Axion couplings constants?
Okay, those are both really excellent questions. So of course, unity has to be unity in some units. And what you're hinting at is that these experiments have different sensitivities. So for example, when we say a coupling constant, we're comparing it really to the strong force. So the strong force would be unity. And then there'd be the electromagnetic force, which is about 1/100th times the strength of the strong force. And then you go down to gravitational force, which is infinitesimal. So a weak interaction would be somewhere in the neighborhood of about 100,000 the strong force, about 10 to the minus 5. So unity for particle physicists, we usually say, okay, if we assign the strong force in terms of how the strong force is able to bring objects together and change their dynamics, we assign a coupling strength of 1 to that. Then when we look at objects that couple via electromagnetic force, how does that compare? Like how if I have two protons together, their electromagnetic repulsion versus their strong force interaction, we could compare the two. And what we find is that the reason we can form nuclei at all is because the strong force is about 100 times stronger than the electromagnetic force. Then if we say, okay, but nuclei do decay, and some of them decay via the weak force, that's where we get neutrinos from, and we try to compare, well, how strong is the weak force compared to electromagnetic and compared to the strong? We find that the weak force is about 10 to the minus 5 down. And then all the way, I think about 10 to the minus 30 is where gravity stands. So we believe that these objects are weakly interacting, which means that they're only about 1,000th the strength of the electromagnetic force. So if I have an object that can interact both with the electromagnetic force and can via the electromagnetic force and can also interact interact with an axion, you would be swamped in the electromagnetic force. Think of it as, so we're made up of protons, neutrons, and electrons for the rest of the audience. And think about a refrigerator magnet. So a refrigerator magnet reacts through magnetic fields that are basically little current loops within the material. But it can stick to the side of a refrigerator in spite of the fact that the entire planet Earth is pulling on the magnet down. So that magnetic force that sticks it to the refrigerator has to be stronger than the gravitational force that wants to pull it towards the Earth. So that's what we're comparing. And what you're asking is basically, we expect the coupling to axions, that is, whatever this field is, we expect how an object interacts with it to be very small compared to the strong force and about 1,000 times smaller than the regular electromagnetic force.
Okay, and we have one more. Is the current experimentally allowed range for axion consistent with QCD axion, i.e. solution to strong CP problem? How is it compared with the allowed range for dark matter searches?
So far, it's still in the range for both CP, for both the CP problem and for dark matter searches. With dark matter, you need enough mass, enough gravity in order to solve the problem of why stars moving really fast through the galaxy don't simply zip out of there. And so even if you have a smaller mass or a smaller coupling constant, you can balance one with the other. So basically you have multiple unknowns. So if the mass of the axion goes down, but it's got a bigger coupling constant, then it could still satisfy both sets of equations.
Okay, thank you so much. Those are all the questions that we have. So I think that if anyone has any last minute questions that they want to answer quickly. Otherwise, thank you so much, Dr. Scarlett. This was a great talk and very easy to follow. I'm sure that we all learned. And thank you everyone again for attending, and we look forward to seeing you at our next talk.
Thank you. I look forward to maybe visiting your next talk and listening in. Thank you very much. And thank you, Lisa and Farrell, for inviting me. You guys
Thank you so much.
Thank
Bye-bye.
you so much. Thank you, everyone.